All right, the fundamental theorem of calculus, it's a big one here. What we're saying is that we have some function f that's continuous on AB. So down here on the graph, you can see this function is definitely a continuous function here, and it's function f. It's on the interval from A to B, so we see it's continuous there. And we're going to define this function as a function of t. And so this y-axis here would be y, or f of t here. And so our graph, you can see, is right here showing that function as a function of t. Well, what we're going to say now is let there be some x value in between a and b. And that x, if we wanted to find the area, say from a to x here, we know we'd write it as an integral because the integral finds area. So this would be the integral from a to x under the graph of f of t dt. So that's how we go through and write the integral, just like we've done in the past. All right, well, this now would become a function not of f, but of x. And so if we wanted to, we could set a separate function, say g of x, equal to this integral. And by doing that, this function g of x would now let us find the area from a to any point x in between a and b. And we could find that area out. Well, the interesting part, or what was figured out, is that if we were to take the derivative of this, well, we would end up with g prime of x. But that also means we would have to take the derivative of the other side. So if we take the derivative of this other side, now we have the derivative of the integral from a to x of f of t dt. And what we found out is that as long as this is a continuous function here, that g prime of x, what we took the derivative on the left side, actually ends up being equal to f of x, the same function here that we had, but now instead of a function of t, it becomes a function of x. And that is a powerful statement, and the reason that it's so important is two reasons. One, it establishes that every continuous function f of x has an antiderivative, capital F of x, or in the case of we were just using g of x. So there's always going to be, for every continuous function, there is an antiderivative. Well, why else is that? Because we're showing that area integrals in the area underneath are connected to antiderivatives, it shows there's a connection between derivatives and integration. So now these are not two separate things. All that stuff we found out with derivatives and the properties we found out about integration and using integrals to find area and the amount of space underneath, there is a connection there between those two parts of calculus. Let's look at what that would mean then. So here's an example. There's a graph of f shown here in the figure, and g of x is a function of x equal to the integral from 0 to x of f of t dt. So you can see this graph here, f of t is this graph. We see that it is continuous here. It is a continuous function, which is important. And so this, any x we put in here, in place of here, we'll find the area from 0 to that location. So what we're going to try to do here is see if we can come up with those values of g of 0, g1, all the way through g of 5, and then kind of sketch out a rough graph of this. So let's make a little table here to do this. So we're going to have our inputs of x, and then we're going to have over here what does g of x come out to be, and remembering that this is actually going to end up being then that integral from 0 to x of f of t dt. All right, so let's start with what would we get if we did 0? Well, that would end up being here g at 0 equals the integral from 0 to 0 of f of t dt. Well, we know from integral properties, anytime your upper and lower bound are the same, you are not accumulating any area. And so what we know here then is that our g of x here is going to just equal 0. All right, let's look at the next one. So if we put in 1 now we're looking at what's g of 1? That would be the integral from 0 to 1 of f of t dt. So on the picture, what that means is how much area are we accumulating from 0 to 1? So that would be, what's that amount of area right there? Well, for this one, lucky for us, that is very easily found just using some geometry. It's a triangle with a base of 1 and a height of 2. We know area of a triangle is half base times height, and so the area of that would be 1. Half of 2 would be 1. All right, let's continue. So if we want to find g of 2 net, or x at 2, that'd be g of 2, which means we're doing the area from 0 to 2 of this under this function. Well, now we are including some more area. So now it's not just 0 to 1, we got to include the area under the curve all the way out to 2. Well, that would be our area before of 1, plus now we are accumulating 2 more squares here, so that would be an area total of 3, just using geometry. All right, let's keep going. So now what's G3 going to be? Well, that's the area from 0 to 3 of f of t dt. All right, so now we are including even more area in here. We're going all the way to 3. Now here we do have this one we can't find with geometry anymore. We got to do a little bit of estimating maybe of what that would be. This is an approximation. So there, well, it's most of a square here, but and this one maybe looks slightly less than half of a square. So maybe we're adding another 1.3 to that. So let's say it's approximately, we're adding another 1.3 square area there, so 4.3. It's an approximation. All right, let's find it at 4. So g at 4. Now it's 0 to 4 of f t dt. So now we're adding some additional area here. Remember, it's the area between the x-axis and our graph there. I did that one a different color because remember that's underneath the x-axis. So the height there is going to be negative, giving us a negative area. We'd also have to approximate that one, but it looks like that area is the exact same amount of area we just added on in the previous one, but now it's negative. So if we subtract that area off, that would bring us right back to the same area we had here of 3. All right, we got one more here, the last one. If we find g at 5 now, that's the area, net area from 0 to 5 of f of t dt. What's that going to equal? Well, here we are, again, we're subtracting, we got some negative amount of area. We've kind of been using 1.3 as that amount. So if we subtract 1.3 from our last total, that's going to give us approximate value here of be about 1.7, it looks like. So that would be our net area. All right, the other part of this, he wanted us to then sketch a rough graph of this. So what is the rough graph of this equal? Let's do it right below here. So we are graphing from 0, and I'm going to use kind of same spacing we had on the graph above. And I'll just label quick 2, 3, 4, and 5. This is the function. These are all functions of x because we were putting x in, and we're graphing like this g of x here. So we're seeing what this g function looks like. So if we estimate where those points are going to be, at 0 it was 0, at 1 it was 1, at 2 it was 3, at 3 it was about 4.3, which on my graph is maybe about there. At 4 it was back to 3. At 5 it was 1.7, which we'll estimate maybe right about there. So this graph looks something like that. Some things we should notice here. On our graph, this point looks like the highest point. That would be our maximum here. My graph got a little off here. I'm going to slide this over here. There would be our graph. So what do we notice about that? Well, why is this one a maximum? Well, that occurred at 3. Well, what do we see is happening at 3 there? Well, that was the place where we went from having positive to negative area there. So that would be why we had the most area under the curve at that point. Also, here's some other stuff we should notice. All the points here were underneath the x-axis. What do you notice about the slope of that line? It's negative. Some other things we see here, this is all these points are above the x-axis. Well, what do we have here? Positive slope. So you can see there is a connection here, and the connection is that this graph right here, g of x, becomes the antiderivative of what we saw up top there. So there's a connection that these are antiderivatives of each other. We'll see in some next examples some of those connections.